On November 4th, 2023, a Gulfstream 695A, registration VH-HPY, operated by Ag Air, departed for a routine aerial survey. Within a few hours, the pilot stopped responding to air traffic control and eventually lost consciousness. The aircraft eventually lost airspeed, did not initiate a descent profile, and crashed, killing the pilot and 2 aerial survey technicians. To study this case, we will apply the Hadon matrix and the human factors analysis and classification system, otherwise known as HFACS. Additionally, we'll discuss the pros and cons of each model and why an investigator may choose one over the other. First, the Hadon matrix. This separates the incident into 3 phases: pre-event, event, and post-event, across 4 interacting factors that contribute to an injury or accident. For example, for the pilot factor, we can see that the pilot's pattern of normalizing the use of the aircraft's emergency oxygen as a continuous supply led to the development of altitude hypoxia as the oxygen supply ran out. Symptoms of altitude hypoxia include a sharp increase in pilot error before incapacitation. This practice contravened the aircraft's flight manual and was a routine deviation from the manufacturer's procedure. A classic example of normalization of deviance, a concept described by Diane Vaughan, where inappropriate behavior becomes culturally normalized within organizations or individuals. These can lead to errors with potentially disastrous consequences. The aircraft factor can be seen as a combination of the intermittent pressurization defect and the aircraft's inability to provide the pilot with automation support in a hypoxic state. Additionally, there was a physical environment and the socio-cultural environment, which includes the poor safety culture in Ag Air. The second model is the HFACS model, developed by Wegman and Chappell. This is a bottom-up analysis of an event, starting with unsafe acts and ending with organizational influences. It expands on Reason's model of latent and active errors by including the conditions of the people at the time of the event and how organizational influence plays a major role. Using HFACS, the following unsafe acts were identified. The pilot made a decision error to use emergency oxygen as supplemental oxygen, the normalization of deviance to operate at unsafe altitudes with known defects, and finally the pilot's skill-based error of reducing engine power without initiating a proper descent. The preconditions included the aircraft technology, which is both an intermittent defect and the inability of the aircraft to provide automation support to the hypoxic pilot, lack of communication from the HOFO to ATC, and while the pilot was developing hypoxia. At a supervisory level, known problems were not corrected but allowed to be managed unofficially. Additionally, operations continued using unsafe practices encouraged by senior management. Lastly, the organization had a poor safety culture with the normalization of deviance practiced from the frontline pilots to the company owner. The organization itself was also not supported by clear, firm policies and procedures that could have prevented more staff from engaging in risky behavior and unsafe acts. Both models can identify the same recommendations, such as hypoxia symptom awareness training, improved defect management procedures, engineering upgrades to the aircraft, better risk assessments, clear requirements, and the issue of normalization of deviance behavior. However, when using the Hadon matrix, it was easier to identify the failure of air traffic control to inform the pilots of their possible hypoxic state. Additionally, using HFACS, the issue of senior leaders encouraging unsafe behavior and of non-specific policies and procedures that support this behavior is readily apparent. The most reliable and effective control in this instance would be installing auto descent or emergency landing capable autopilots. Engineering solutions such as this would be more effective at saving lives than additional procedures. Using both models, they appear to identify the same causal factors and draw the same conclusions about proposed systemic changes. This may be due to the same person completing both assessments, which guarantees bias in interpretation. However, both models are easy for trained investigators to use. It should be noted that the Hadon matrix appears to be more widely used in medicine and road traffic, while HFACS was developed for aviation. As Wegman and Chappell state in their original research on HFACS, it is not an investigation tool meant to stand wholly on its own. It lacks the ability to sequence events and provide comprehensive insight into an event. Hadon's matrix suffers from similar issues and cannot comprehensively review all factors that we recognize today in aviation.